Physics Bites,
a science podcast in English by the students of Notre Dame d'Ascension.
Hello and welcome again to a new episode of Physics Bites, the physics podcast in English from our students at Notre Dame d'Ascension in Paris. We have two new students today who are going to talk to us about the history of gravitation. Do you guys want to present yourselves?
Yes. Hi, my name is Lisa.
So we have Lisa who worked on the presentation, and we have a substitute today.
Hi, I'm Zaïnab.
And Zaïnab who's substituting in for Lola who wasn't feeling good this morning. And so we have a different combination. We're going to hear Zaïnab again in a few episodes. She's going to talk to us about time travel. I also have a co-host today that you heard last week. Do you want to present yourself, co-host?
Hi, I'm Sixtine, and you saw me last week for the trip to Mars episode.
Right, you guys were talking about how to get to Mars and potentially stay there. So, how about we get started as usual? I'm going to ask Lisa to give us a little summary of your presentation on gravitation and the history of gravitation, and then we'll get into the questions from your classmates.
All right. So, as you said, we talked about gravitation and its history in general. We firstly talked about what is gravity and its general definition, with the fact that it can be mathematically represented by a formula.
Right.
And then we talked about the theories from Aristotle to more
modern interpretations
exactly
of
what is gravity and
right. I think it was interesting that you guys made the choice to talk about Aristotle to begin, because technically he didn't call it a theory of gravitation. He was just trying to explain why things fall and some things float. But I guess it does fall into part of the history of how we try to explain this phenomenon, which is finally now called gravitation. So do you want to talk to us a little bit about what Aristotle's quote-unquote theory of gravitation was?
Yeah, so, all right. Aristotle, so he was a Greek philosopher, mathematician,
scientist, everything. Just an all-around wonderful guy.
Exactly. And he described two kinds of motion, the violent or unnatural motion and the natural motion. So for the unnatural motion, for example, such as the thrown of a stone, according to him, as soon as the agent stops causing it, the motion also stops. And in other words, the natural state of an object is to be at rest, since Aristotle does not add friction to the object in question.
Right, and the agent here is referring to the person throwing the rock?
Yeah, exactly.
Okay. So how does he describe stuff falling, stuff going up in the air? What was his explanation or his theory, if we can call it that?
Well, he believed in the elements, in the four elements, the elements fire, earth, air and everything.
And water.
Exactly.
Yeah, everything.
Thank you. And so he said that objects fall because each of the four elements had their natural place, and these elements had a tendency to move back to their natural place.
Right. So each of the four elements, we can divide up the universe into four layers where, for example, which is the most low, I guess, the lowest of...
So we have Earth and water. The place is the center of the geocentric universe.
Right.
And the natural place of water is like a concentric shell around the Earth, because Earth is heavier and it sinks in water.
Right.
And the natural place of air is likewise a concentric shell surrounding that water. Yeah.
And fire would be the highest of them all, exactly. The most exterior. So how does that explain, for example, why if I pick up an object, if I pick up my phone and I let it go, why does it fall, according to Aristotle's theory?
Well, because it falls because it's attracted to the Earth, and that he states that every object, like I said, had a tendency to go back to where they come from.
Its natural place. Yeah. So in that explanation of the universe, then my phone, by the virtue of going back, of falling in water, would be mostly made up of Earth, right? And if, for example, fire, if we heat something up and it goes up, it's because fire wants to go to its natural place, which is above air, and that's how it explains floating. It's a very interesting idea, very ingenious for his time, but clearly not how we see the world today. So what is the next step in the history of gravitation? How far do we have to go into the future from the time of the ancient Greeks to reach it? I guess we can go through the medieval period and we get to the Renaissance, and I guess Galileo.
Yeah, and Galileo also, he talked about these, he kind of developed Aristotle's theory. And so he developed this theory, and he found that all objects tend to accelerate equally in free fall.
Right.
Because Aristotle didn't know that when an object fell, I think he thought that every object fell at the same, not the same...
with the same acceleration.
With the same acceleration. And Galileo found out that all objects tend to accelerate equally in free fall.
Right. This is the famous story about Galileo letting go of two objects from the top of the Tower of Pisa, one like a tiny little ball and a big metal ball, and they both fall at the same rate, which is basically what we call today maybe the beginning of mechanics and study of mechanics, which was then further developed and formalized by Isaac Newton, who also had the first true theory of gravitation in the modern sense. Do you want to talk to us about that a bit, maybe?
My colleague talked about
Lola,
Newton,
who's not here.
Lola, who's not here, and she also talked about Einstein.
Right. Maybe Zaïnab, you want to take over here and fill in the role of Lola, who's not present?
So basically, Newton, he created a formula which says that the gravitational pull is equal to the constant of gravitation.
Right, what we call the universal gravitational constant.
And then it is multiplied by the mass of the two objects that interact with each other.
Right, so according to Newton, you can't have gravitation if you don't have at least two objects with a non-zero mass.
And it's divided by the half of the distance.
The square of the distance.
The square of.
So two things that are 2 times further apart, the gravitational pull is 4 times weaker, 3 times apart, 9 times weaker, and so on. It's a pretty good theory, right?
Yes, but
it's working pretty well, or no? Maybe it's not working so well?
It's worked for the most part for classical interstellar object, but it was then... there was another theory that was developed by Einstein, which explained the universe more accurately.
Right.
And it's like the theory of the gravitational, the theory of relativity.
Right, general relativity that two of your classmates, Marc-Antoine and Marc-Alexandre and Antoine, talked about last time when we were talking about cosmology. Are there any further developments since gravitation according to Einstein, or is that kind of the end point?
I think it's kind of the end point.
It's kind of the end point, at least in your presentation. We're working on what we call a quantum theory of gravitation. We haven't gotten there yet, but at least for your presentation, it was a pretty good sort of summary of the development of these ideas. Of course, the actual history is much more detailed. Is there anything more you want to add, or shall we move on to the questions?
No, that's it.
That's it? All right. So, Sixtine, do you want to start asking a few of the questions? Maybe your own questions as well.
Right. So, for now, we focused on Galileo and Newton's theories, but, do we have any knowledge of, notions of energy, momentum, or other theories that existed before them?
Well, we talked about Aristotle before, and the fact that he uses kind of his own beliefs to make up his own theory, but his theory is not as well defined as Einstein, for example's theory, because he didn't have the same mathematical tools.
But he didn't have the same mathematical tools. He didn't have the same sort of physical knowledge. And I think the one important thing, what we shouldn't forget, is that the way we do modern science with lots of experimentation and this sort of the empirical method, it didn't exist at the time. So they were often content to just think about things and just leave it at that without actually going and testing, formulating a hypothesis, and then coming back and seeing if it worked or not. So it was a completely different way of doing things, which for us has helped us move along scientifically, and for them, I guess it was not quite yet developed. These ideas of movement, I guess, and acceleration and momentum, that does come back to the period before Galileo, but Galileo was, I guess, the first person who really formalized it and talked about it in a very mathematical way. Any other questions, Sixtine, that drew your attention?
Yeah, was Einstein's theory like vastly different from Newton or Galileo, or were there like lots of similarities, or did he really break away with the theories?
It was kind of a breakthrough. So basically, in Newton's theory, there was like gravitation, and the space-time was like a flat sheet. However, with Einstein, he said that the mass of an object can deform the space-time, and so the gravitational pull is caused by the mass of the object, and it's caused because the space-time is curved. However, Newton's couldn't explain why gravitation really existed, and Einstein could, so that's kind of a breakthrough.
So the interesting thing, I guess, is that for the most part, they make the same predictions. They give the same results when we want to talk about how the moon is going around the Earth and stuff like this. But the way they explain how it happens are very different. Like you said, is that in one case we use the notion of force in the case of Newton, whereas in the case of relativity, we don't need to talk about force. We're talking about just curvature of space. So that's where it was a big breakthrough. Do you, either I can ask a question to Zaïnab or to Lisa, did you guys find out why it was that what inspired Einstein to break away from the Newtonian way of looking at things? Or if something is working really well, why come up with something new? No? I guess we would need Lola for that. Yeah. Well, the idea, I think, with that was that Newton's theory didn't explain everything. Notably, there were 2 or 3 phenomena which were not explained by it. For example, the fact that Mercury turning around the sun doesn't have a perfectly stable orbit. It's what we call a precession. It wasn't explained by it. All right. Sixtine, what other questions did you see which were kind of interesting?
Yeah, how did, going back a bit in time, how did religion, or the belief of geocentrism, slow the discoveries about gravity? How did that time period's beliefs, affect scientific research?
What is the link between the religious state of the times and how, if at all, it interacted with the science of the times, which led to slowing down of maybe something or speeding up of something else in general?
Mm-hmm. Well,
so we're talking about a bit of history, I guess.
Yeah. So I know that religion had, you talked about religion, it played a significant role in showing the discoveries about gravity. And in particularly during the Middle Age, when the church promoted the idea of geocentrism. And
can you just tell us what that is, this idea of geocentrism?
I guess it's the idea that...
I guess the center of the universe is the Earth.
Is the Earth.
And everything is going around it.
Yeah, everything's... Basically, the Earth is the middle, the universe.
Right, which was, I guess, appended when Copernicus came up with his, I guess, called theory of heliocentrism, right? With the sun at the center, because it made it easier to calculate the way we could predict the movement of the planets and stuff related to that.
Yeah, there was also this other guy named Johannes Kepler.
Johannes,
exactly. Who showed that the planets moved in elliptical orbits around the sun also. Right,
and this was before Newton, before the modern form of gravitation. But the interesting thing is, well, for those of you guys who are doing physics this year, like Zaïnab, you guys found that when we study... Do you want to talk to us about what is the link between Kepler and Newton? Maybe what did you guys find that was interesting?
Yes, I think what's interesting is we can use like Kepler's laws to predict the precession, not the precession, but the time that a planet goes around.
The time of revolution, right?
And
period of revolution.
Yeah, and we can link it to Newton's law with to calculate, for example, the acceleration or the speed of a planet.
One of the more interesting things about Kepler is that what he found with his famous third law is that all the, for example, planets that turn around the sun, their speed is and their distance from the sun, there's a proportionality law there, and this proportionality law is constant for all the planets turning around the sun. And he had this intuition to say, I think there's something going on. There's some sort of a connection between the sun and all these planets. Otherwise, there would be no reason for them to sort of follow this sort of uniformity in terms of their behavior. And in a way, I guess, by intuition, he foresaw the description of what we call gravitation. And the interesting that you guys did also in class is that when we use Newton's laws of motion, we can come up with Kepler's laws by just pure calculation, which sort of confirms what Kepler found empirically, and it sort of validates also Newton's theory, which is kind of very, very interesting. I find that part of the classwork pretty interesting to see. We come from 2 points that are very different to arrive at the same conclusion. It's kind of a fun moment. I guess, Sixtine, you had a question yourself. Do you want to ask directly?
Sure. I was wondering if light and matter were affected the same way through space.
Yes and no.
According to which theory? Because there's only one theory that takes into account
I would say Einstein theories would take in account like that, for example, light can be deviated by the gravitational pull of a planet.
Or a star, planet, anything,
anything that has a mass.
Which was not predicted by Newton's theory, right? It's only general relativity that predicts that.
And of course, like mass can be deviated by the gravitational pull of other planets. And so light was by Eddington showed the...
So Arthur Eddington, who was a famous physicist and astronomer, who did a test, one of the first tests of
to prove
general relativity in 1918. And what did he do?
It was during a solar eclipse, and he wanted to calculate. There were like two laboratory.
I guess two observation or labs,
that calculated the distance and the place of
the position of a particular star.
And it was later proved that the star was like slightly away from its supposed place because the light was deviated.
So they chose a star which would be during the eclipse, normally behind the sun. And the fact that they were able to see it was because the light coming from behind the sun was able to bend enough to go around and reach the observation area, kind of proving that Einstein's theory about light being affected by gravitation was true. And not only that, but also that the exact position that the theory predicted was what they observed, which is kind of the ultimate form of validation of a scientific theory. I don't know, Sixtine, do you have any more questions for your classmates?
Maybe, like, we've said this before, but could we, like, suppose that there's a relation between, like, matter, light, and time, since they all kind of are affected in different ways by gravity?
Yes.
Yes, because I guess in Einstein's theory, how do we look at space and time?
It's time depend of the mass of an object. For example, the more an object is massive, the more time will go like slower. It's slower.
Right. Because we don't separate space and time anymore. So if space is affected by the presence of a mass or energy, then so is time. So in a way, everything is mixed up together. So Lisa, what did you find particularly interesting during your research? Was there stuff that you discovered that you didn't know before, which were particularly interesting or striking? What did you think about? Because I think it's important to say that you haven't done physics since grade 10. It's been a couple of years, but you've been in our physics and English class, so you don't have necessarily the same training as some of your classmates. But you've always picked out interesting topics. What was the topic you did last year?
It was Fahrenheit.
No, it was Faraday.
Faraday cages.
Yeah,
Michael
Faraday.
Faraday. That's right. That's right. Because you guys did together with
Faraday,
16. So I guess you're at a bit of a disadvantage compared to many of the other classmates, but you've done a good job. So what did you find interesting in your research for this presentation?
I guess everything was interesting in general because it's the whole history of gravitation in general. And I guess I already kind of knew Einstein's theory, but like really basic stuff.
Right.
But I really liked Aristotle's point of view.
Right. It's I think because you're doing more humanities and literary subjects this year, and Aristotle I think is more present in what you study than somebody like Einstein. So it is interesting to see how the reasoning was going at the time.
Exactly.
And if we had more time, we could go into it a bit more, but it's okay. So I guess 16, you have no more questions?
No.
Okay. Lisa, do you want to add anything? Do you want to say anything in the place of your absent classmate Lola?
No, I'm good.
You're good? All right. Zainab, thank you for filling in at the last minute. It's never easy, but I think you did a pretty good job. Thank you, Lisa. Thank you to my co-host, 16, and we'll have a new co-host next week. So thank you for listening, and see you next time. Bye, guys.
Bye.